Now I am going to discuss the design procedure of a laterally supported beam. So in last lecture we have discussed how to calculate the design bending strength of a laterally supported beam, how to calculate the design shear of a laterally supported beam. So in today's lecture, first I will go through very quickly the design steps for laterally supported beam, and then I will go through one workout example. So in first steps, what we can do, we can find out what are the load acting on the beam, and then we can calculate the appropriate load by multiplying the partial load factor. So whether it is due to dead load, live load, or due to wind load or seismic load, depending on that we can find out what is the load coming and what will be the partial load factor. So from that we can find out the bending moment distribution and shear force along the beam length, and then from that we can find out maximum bending moment and shear force, because I have to design the beam against the maximum bending moment and maximum shear force. So on that basis, then I can find out a trial plastic section ZP as MD by Fy by gamma m0. Considering whether it is high shear or low shear, irrespective of that, first I will find out a trial plastic section from this formula, that is Zp is equal to Md by Fy by gamma m0, where Md is the maximum bending moment which we have calculated, Fy is the yield stress of the material, and gamma m0 is the material safety factor, right. So from this we can find out a trial plastic section, and then we can select a suitable section. So from the plastic section modulus we can find out a corresponding section, whether we are going for ISMB or ISLB, depending on that we can find out a section whose plastic section modulus is greater than this, slightly greater than this. Then we can classify the section as plastic, compact or semi compact from table 2, right, compact, semi compact or plastic. So depending on the B by TF ratio and D by TW ratio, I can find out from table 2 that whether the assumed section is plastic or compact or semi compact. Once it is done, then I can find out the design shear strength Vd. Vd will be calculated as Fy by root 3 gamma m0 into H into Tw. H we can write, or D, earlier I have told D, where H or D is the overall depth, right. So design shear strength Vd can be calculated from this, and then I will check whether it is high shear or low shear. If the V is less than 0.6 Vd, then the beam will be low shear, and if it is more than 0.6 Vd, then beam will be considered as high shear. So considering high shear or low shear, the formula will be different for calculating design bending strength. So if it is low shear, then I can find out Md value as this, that is beta b into Zp Fy by gamma m0, right. So now for a particular section we know Zp value, and depending on the type of section, whether it is plastic, semi plastic, plastic, compact or semi compact, I can find out the beta b value, and gamma m0 value I know. So from that I can find out the design bending strength Md, and it has to be less than 1.2 Jd Fy by gamma m0, and for simply supported beam, and for cantilever it has to be less than 1.5 Jd Fy by gamma m0. So in these steps we could calculate the design bending strength for low shear, and for high shear the design bending strength will be calculated from this formula, where MdV is equal to Md minus beta into Md minus Mfd, and it has to be less than or equal to 1.2 ZD Fy by gamma m0, and this is for plastic and compact section, and for semi compact section MDV can be calculated as ZD Fy by gamma m0. So, MDV value for high shear can be calculated depending on the type of section from this formula. And now, if we see that M is greater than MD, then we have to increase the section size and repeat from step 5, right. That means, if the design bending strength is less than the actual moment, then I have to increase the section size and then I have to repeat from step 5. Otherwise, if it is satisfying, then we can go to step 9. So, from step 5 to 8 will be repeated till the design bending strength is more than the bending moment, developed bending moment. So, if it is more, then fine, otherwise I have to repeat, and once it satisfies, then I will calculate the I will calculate the design shear strength Vd, and it should be greater than the maximum factor shear developed due to external load. So, maximum factor shear V has been already calculated. So, and the design shear strength should be greater than this. If this is fine, then we can go to next step. Otherwise, if V is greater than Vd, then redesign the section by increasing the section size. So, if we see that the shear is more than the design shear strength, then we have to redesign by increasing the section size. And next step, we have to check for deflection, which is also another important aspect, that is the beam has to be checked for deflection as per table 6. In table 6, the limiting deflection criteria has been given, and the maximum deflection can be calculated from the given boundary conditions and the loading conditions. So, from that we can find out the maximum deflection, and maximum deflection has to be less than the limiting deflection given in table 6. If it is okay, then fine, otherwise we have to again increase the section. Now, we have to check for wave buckling. The beam needs to be checked for wave buckling, that is, if we see that d by Tw ratio is less than 0.67 epsilon for without for wave without stiffener, then the wave is assumed to be safe in wave buckling and we do not need to check. So, the shear strength of the wave is governed by plastic shear resistance, and the wave should be checked for buckling in case of high shear, even if this limit is satisfied. And the wave buckling strength can be calculated, we know, that is Fwb is equal to Ab into Fcd, where Ab is the area of the wave at the neutral axis, that is B into Tw, and Fcd is the design compressive stress, which can be found from table 9C, because it is buckling class C. So, from this I can find out the wave buckling strength, and this wave buckling strength should be greater than the design shear force at that point, right. So, if wave buckling strength is greater than the design shear strength, then fine, otherwise we have to increase the bearing plate length. Either we have to increase the bearing plate length or we have to increase the section size to increase the wave buckling strength. So, once it is okay, then we will go for checking wave crippling. Wave crippling, that FWC, wave crippling strength, this has to be also less than the shear force at that point, and FWC, the wave crippling strength, we can calculate from this formula, that is B1 Tw Fyw by gamma m0, where B1 is the dispersion width and Tw is the thickness of the wave and Fyw is the yield strength of the wave, right. So, wave crippling strength FWC can be found from this formula, and it has to be more than the shear force coming on that section. So, if it is satisfying this criteria, then fine, otherwise again we have to increase the section size or we have to increase the bearing length to make the section safe from the wave crippling. So, these are the steps which we need to follow to design a beam with laterally supported. So, now we can go through this example where a cantilever beam of length 4.5 meter supports a dead load which includes self weight, that is 18 kilonewton per meter, and a live load of 12 kilonewton per meter. Assuming a bearing length of 100 millimeter, design the beam. So, a cantilever beam we have to design where the length of the member is 4.5 and load is given 18 kilonewton and 12 kilonewton as dead load and live load, and we have to assume the bearing length as 100 mm, and accordingly we have to design the beam. So, let us come to step 1, in which we have told we have to find out the dead load with load factor. So, dead load 1.5 into 118 and live load also 1.5 into 12, which was given. So, this will be 27 kilonewton per meter and this will be 18 kilonewton per meter. So, total load, dead load plus live load into 1.5 times W is equal to this is equal to say 45 kilonewton per meter. So, in step 1 we have calculated the factor load W, which is coming 45 kilonewton per meter. Now, we will go to step 2. In step 2 we can find out the maximum bending moment as WL square by 2 for cantilever beam. Maximum bending moment will be at the support. So, W is 45, L is 4.5 by 2. So, that is becoming 456 kilonewton. Similarly, the maximum shear force will be at the support, that will be W into L. So, 45 into 4.5, that will be 202.5 kilonewton. So, in step 2 the maximum bending moment and maximum shear force we have calculated. Now, we have to choose a trial section. So, in step 3 we can choose a trial section. For that we can find out ZP required, that will be M by Fy by gamma m0. M is 456 kilonewton meter, 456 kilonewton meter. So, 456 into 10 to the 6 Newton millimeter by 250 by 1.1. So, this is becoming 2006.4 into 10 cube millimeter to the okay. So, in step 3 we could find out the ZP required, and now we can find out a suitable section from SP6, and if we look into XP6 we can say that ISLB 550 at 0.846 kilonewton per meter, we can choose this section whose ZPZ is equal to 2228.16 into 10 to the power 3 millimeter cube. We need 2006 and we are providing 2228, right, and ZEZ here will be 1933.2 into 10 to the power 3. So, these values are obtained from SP6, right, and also we could find out D value as 550, the overall depth, width of flange 190 mm, thickness of the web 9.9 mm, thickness of flange 15 mm, and root radius r we could find 18 mm, right. So, from this also I can find out the d value small d, that will be 550 minus 2 into Tf plus r is equal to 550 minus 2 into Tf is 15 minus 15 plus r 18. So, this is becoming 484 millimeter, and also IZZ value we can find from the SP6, that is 53161.6 into 10 to the 4 millimeter to the 4. So, these are the data which will be required to calculate the design bending strength and other details, right. Also, I have to find out what is the section here, whether it is plastic, compact or semi compact. So, now here we know Bf by here Bf by 2 by Tf is equal to, it will be Bf we found as 190 by 2 by 15 is the thickness of flange. So, this is becoming 6.33 and this is less than 9.4. Similarly, d by Tw we are getting 484 by 9.9 equal to 48.9 less than 84. Okay. So, from this I can say this is a plastic section. So, if it is plastic section, then I can find out the value accordingly, right. So, now in step 4 also I have to find out that what is the shear capacity Vd, because before calculating the bending moment, bending strength of the section, we need to know whether it is high shear or low shear. So, for that we have to find out what is the design shear strength of the section, and also we have to know whether it is plastic, compact or semi compact. According to that, the beta V value will be calculated, right. So, here Vd will be Fy by root 3 gamma m0 into d into Tw. So, I can put those value, that is d is 550 into Tw is 9.9. So, these values are 714.47 kilonewton, right, and 0.6 Vd is coming as 0.6 into 714.47, this is 428.68 kilonewton, which is more than the V, and V value is coming 202.5 kilonewton, right. So, what we could see that here the design shear strength is becoming 714 kilonewton and 0.6 Vd is coming 428, which is more than V. So, it is low shear. So, you can see this is as low shear, because shear force is coming less compared to the design shear capacity. Okay. So, if it is low shear, then I can find out the design bending moment design bending strength accordingly. So, in step 5 I can find out design capacity of the section, design moment capacity of the section, that is Md. So, Md will be simply Zp Fy by gamma m0. So, Zp value we find earlier, which is this, Fy is 250 and gamma m0 is 1.1. So, this is 506.6 506.4 kilonewton meter, and it has to be less than, as it is a cantilever beam. So, it has to be less than or equal to 1.5 to J d into F y by gamma m 0, that is 1.5, J d is 1933.2, 10 cube into 250 by 1.1, right, that is 659 kilonewton. So, M d is this, M d is less than this. So, we can consider the design bending strength of the section as 506.4 kilonewton, right. So, next we will find out, and this is more than the moment coming, maximum moment coming, right. So, okay. Now, in step 6 we can check for deflection. So, check for deflection, delta we know, that will be W L to the 4 by 8 E I. This will be the maximum deflection for cantilever beam. So, if I calculate, W will be 27, because this will be under service load. So, it will be 27 into 4 5, W will be 18 plus 12, this will be 30 into 4500 whole to the 4 by 8 E is 2 into 10 to the 5 into I we found earlier, that is 53161.6 into 10 to the 4, right. So, this is coming around 14 mm, right, and allowable deflection, we can find out allowable deflection. Allowable deflection will be L by 150, that is 4500 by 150, that is 30 mm. So, which is more than the actual deflection. So, it is okay. So, from deflection point of view also, the section which is assumed is fine. Now, we will go to next step, that is step 7, which will be dealt with wave buckling. So, you have to see whether it is buckling, means wave, its wave is buckling or not. So, the cross sectional area of the wave for buckling, that is A B, we can find out, that is B 1 plus N 1 into T W, because at the support only it will be, and B 1 is actually B 1 is 100, okay. B 1 is given as bearing length, that is 100 mm, and N 1 will be D by 2, that will be 550 by 2, 275. So, A B we can find out, that is 100 plus 275 into T W as 9.9. So, cross sectional area of wave for buckling will become 3712.5 millimeter square, and effective length of wave L E is equal to 0.7 D, that will be 0.7 into D we calculate earlier 484. So, this is becoming 338.8 millimeter. Now, I can find out moment of inertia I. So, I will be B T cube by 12. So, B has been considered as 100, T is 9.9 by 12. So, this is becoming 8085.8 millimeter to the cube. and area we can find out, this is as 100 into 9.9, so 990. Right. So, R minimum I can find out, R minimum will be I by A. So, I is 8085.8, cross section area is 990, this is becoming 2.86, and lambda I can find out L by R, L effective by R minimum. L effective we found 338.8, R minimum is 2.85, so this is becoming 119. So, allowable stress FCD for lambda as 119, Fy as 250 and buckling class as C. So, from table 9C I can find out the value of FCD. So, FCD value is coming as 84.8 Newton per millimeter square. So, this is obtained from table 9C. So, capacity of the section I can find out, capacity buckling strength I can find out as FCD value 84.8 into area 3712.5. So, this is becoming 314.8 kilonewton, and that is greater than the maximum CR, which was coming 202.5 kilonewton, right. So, it is okay. So, the section is safe against wave buckling. Now, next step I will go, that is step 8, wave crippling. We have to check for wave crippling. So, for wave crippling I have to find out the wave crippling strength Fw is equal to B1 plus N2 into Tw into Fy by gamma m0, right. Here N2 will be 2.5 into R plus Tf, because it will disperse with 2.5 slope, 1 is to 2.5 is to 1 slope. So, 2.5 into R was 18, thickness of flange was 15. So, this is becoming 82.5. So, B1 we have considered 100 mm length of bearing. So, 100 mm plus 82.5 as N2, and thickness of wave is 9.9, then 250 by gamma m0. So, this is becoming 410.6 kilonewton, and this is greater than 202.5 kilonewton. So, the section is safe against wave crippling, right. So, this is how we can find out the wave crippling strength, and we can see that the section is safe against wave crippling. So, from this what we can see, that we have to design the beam stage by stage. So, the steps are discussed earlier. So, according to these steps we have gone through, and we have checked every step that whether the assumed section is safe against moment, against shear, against deflection, against buckling and against crippling. So, all the checks are satisfied. So, the section which are assumed is okay. So, whatever I have done, I am quickly going through this through the PowerPoint presentation, so that we can keep note. Say for example, here in first step we have calculated the load, factor load, which is coming 45 kilonewton meter per meter, 1.5 times dead load plus live load. and then we have found the maximum bending moment, which will be W L square by 2, and maximum shear force, which will be W L at the support. So, maximum bending moment and maximum shear force are calculated in step 2. Then we have to choose a trial section. So, for that we can find out the plastic section modulus required, which is m by f y by gamma m 0, and from that we can find that the ZP required as 2006 into 10 cube millimeter cube. So, this is the required of ZP, and we will try to choose a section such that its ZP value becomes little higher than the required one. So, through SP6 we could find a section whose size is ISLB 550 and its ZPZ is becoming slightly more than the required one, that is 2228.16 into 10 to the 3 millimeter cube. And also we found the value of ZEZ, then the overall depth, small d we can find, and also we can find the TF, TW, root radius, and IZZ, right. Also we can find the section classification. So, from section classification we can see it is less than 9.4 and less than 84. As a result, this section is a plastic. So, the ISLB 550 when we are going to use, it will be a plastic section and its properties are given here. So, considering this property, we can now find out the shear capacity of the section in step 4, that is Vd is equal to Fy by root 3 gamma m 0 into area, shear area, which is H into Tw. So, this value is coming 714 kilonewton, and 0.6 times of that is greater than the developed shear, therefore, it is low shear. So, for low shear, the design capacity of the sections can be calculated from this formula, where MD is equal to ZP into Fy by gamma m 0. So, we can find out the MD value as 506.4 kilometer meter, which is greater than the developed moment, okay, WL square by 2. So, it is okay, and then also we have to check whether it is less than this or not, 1.5 ZD Fy by gamma m 0. There we can see that ZD Fy by gamma m 0 is 659. So, MD value can be considered as this. Now, we will go for check for deflection. So, for deflection we will find out delta is equal to WL to the 4 by 8 EI. W will be 30 into 4500 to the 4 by 8 EI. Then its value we have to check, maybe around 14 mm it will be, and allowable deflection is coming 30 mm, which is much higher than this, right. So, from deflection point of view, the chosen section is safe. Then we will go for wave buckling, and as the bearing length was given 100 mm. So, I can find out the cross sectional area of the wave for buckling. So, for that B1 we know and N1, because if this is bearing, then it will be dispersed 45 degree up to neutral axis, and this is d by 2, right, which is N1. So, N1 is d by 2 is 275. So, area of the wave for buckling we could calculate, and effective length of the wave is 0.7 d, where d was calculated earlier. So, we can find out I value, A value, and then I can find out the R minimum as 2.86 and then lambda, right. Once lambda is found, we can find out the value of allowable stress FCD, because corresponding to this lambda and with buckling class C for Fy is equal to 250, the allowable stress is becoming 84.8 from table 9C. And then capacity of the section can be found from the FCD into AB, and it is becoming more than the shear force coming on the support. So, the section is safe against wave buckling, and then we will go for wave crippling. So, crippling strength also we can find out. Fw is equal to B1 plus N2 into Tw into Fy by gamma m0, and N2 will be calculated with a dispersion of 2.5:1. So, and it will be calculated if this is the wave thickness, flange thickness Tf, and if this is the root radius, then up to this, right. So, this will be N2. So, N2 value is becoming 82.5, and then I can find out the crippling strength, which is becoming 410 and is more than 202 kilonewton. So, the section is safe against wave crippling as well. So, this is how all the checks are performed, and the size of the section which has been assumed is safe, right. So, this is how we can design a section under low shear with its means which is support means laterally supported beam, means if it is laterally supported and low shear, then how to design, that has been demonstrated through this example. Okay.